Hi, today I'm going to talk about the pseudorandomness of expanded random walks for symmetric functions in permutation branching programs. And this is from joint work with Salil Vadan. So just to give an overview, expanded graphs are graphs that are simultaneously sparse but well connected. And here we're going to study the pseudorandom properties of random walks on expanded graphs. So this general area has been well studied and applied to numerous different areas and different problems. And the specific question we look at, to what extent do expander walks fool specific classes of test functions? So specifically symmetric functions and permutation branching programs. This question has also been investigated by a line of prior work, including these recent papers by Guruswamy and Kumar, and then a couple by Cohen et al. And our results generalize and strengthen results for symmetric functions and permutation branching programs in these prior works. So our main result states that random walks on lambda spectral expanders fool symmetric functions up to a big O of lambda total variation error and fool permutation branching programs up to a big O of lambda L2 error. So for both of these results, we improve upon the prior work. We also show lower bounds to show that these results are tight. And we also show a number of generalizations and strengthenings. For instance, we unify our bound for symmetric functions with a tail bound, so the total variation and tail bound together, which gives a slightly strengthened version of the expander walk turnoff bound. So before getting into more details on these results, I'll just review the basics behind expander graphs. So for the purpose of this talk, an expander is simply a regular graph with a random walk matrix G. So here we'll interchange kind of Buse notation and interchange a graph with this random walk matrix. But here we look at spectral expanders. So the spectral expansion is simply the maximum, or I guess the spectral norm of the random walk matrix G when we restrict to vectors that are orthogonal to the all ones vector. So intuitively, the all ones vector, or the uniform distribution, is the stationary distribution for our random walk. And good spectral expansion, which means a small lambda here, means that the random walk matrix significantly contracts all vectors orthogonal to the stationary uniform distribution. So if we apply the random walk matrix many times, which corresponds to many steps in the random walk, we'll rapidly converge towards the uniform distribution. This is really the intuition behind spectral expander graphs. And typically we'll take constant degree spectral expansion bounded away from 1 and arbitrarily many vertices. And in this regime, expander walks actually give randomness efficient approximations to truly random sequences of vertices. So I guess the idea is, since the degree is constant, at each step in the random walk, we only need a constant number of bits of randomness to perform this random walk. But we're rapidly approaching the stationary distribution, and more generally, as we'll see throughout the talk, in many cases, this expander walk actually is quite a good approximation to just truly like a random walk on a complete graph. So I'll next describe our problem, which, as I mentioned, arises in many different areas in theoretical CS and has been studied before. And I'll describe some of this motivation after stating the problem. So we're given a lambda spectral expander G with a Q-area vertex labeling. Often it's best to think about binary labelings, but most of our results generalize to arbitrary fixed Q. And we're also given a class of test functions F, which take as an input a length T sequence of labels and output some value in S. So I guess this output family, it could be binary, it could even be all the integers, something like that. And our goal is to bound the total variation distance between the two distributions. One of them is F applied to the labels. So the output of F when applied to the labels from a length T random walk on G, in comparison to the output of F when applied to the labels from a length T random walk on the complete graph with self loops J. So I guess just to illustrate that, we're comparing say we could take a random walk on G here, get the label something like 0, 1, 0, 1. Or we could also do a length for instance, with t equals 4, we could get like maybe 0, 1, 0, 0 on J. And so we get these two probability distributions. We pass them through F, and we compare the resulting output distributions. And we want to kind of bound the maximum total variation distance between these two output distributions on any test function F from our class. Now we're often going to be looking at symmetric functions. So these are functions where the output does not depend on the order of the inputs, which, at least for binary labelings, our results apply to more generally to arbitrary Q-array labelings, but it's easiest to think of binary labelings where symmetric functions simply means that the output depends only on the sum of the inputs, so the number of ones in our input string. And in this case, it's sufficient to restrict attention to just the single symmetric function, which just adds up all the input labels. So we want to compare the total variation distance of the sum of the labels from a random walk on our expander G versus the sum of the labels from a random walk on the complete graph J. And just a notational point, we'll often write this kind of dropping the indices, but this is really the same thing. So the motivation from this work comes from the fact that this exact problem seems to arise in many different settings in theoretical CS. It's actually been an ingredient in some pretty important prior works. So one example is the expander walk turnoff bound, which states that the sum of the labels from a random walk on an expander graph is highly correlated around its mean. So that's basically saying this distribution up here has rapidly decaying tails, just as the ordinary turnoff bound says that this distribution down here has rapidly decaying tails. So basically, the expander walk turnoff bound says these two distributions have similar tails. In fact, one of our results will show that, will strengthen this result and show that these tails are actually essentially even more closely related than was previously known. Another motivation is error correcting codes. So actually, Tashma's breakthrough construction of almost optimal epsilon balance codes is based in the previously known fact that the sum of the labels from a random walk on an expander, when taken mod 2, converges exponentially quickly towards a 1/2 Bernoulli, which is what we get when we take the sum of the labels from a random walk on the complete graph mod 2. This is actually the binomial distribution modulo 2. And one of our results for permutation branching programs, which I unfortunately won't have time to talk about here, actually generalize this result, for instance, to larger moduli. And I guess the third motivation is pseudorandomness. So our results for permutation branching programs are largely motivated by work like in the small space derandomization literature. They're actually quite closely related to some work on the INW generator. And I'll talk about this more in a bit. Unfortunately, our work does not directly give better PRGs, but we hope our techniques could be applied to that in the future. Okay, so next I'll state, so in the next few slides, stating our main results. First, for symmetric functions, so we show that for every lambda spectral expander G with a vertex labeling, here I wrote binary, but some of these results basically generalize to Q-array, or at least this total variation bound here. So we show the total variation bound that the total variation distance between the sum of the labels from a random walk on our expander G and the sum of the labels from a random walk on the complete graph J has total variation distance at most big O of lambda. And we actually generalize this to show this tail bound on top, which basically states that if we restrict attention only to coordinates that are far away from the mean P1, say distance C away from P1, and then take the total variation distance on these tails, we still get the big O of lambda bound, but we also get to multiply it by this exponentially decaying factor. So the tails, the tails of the difference decays very rapidly. And this total variation bound is tight. So we do prove a matching lower bound. Actually, a similar matching lower bound was previously known in the literature. And our tail bound here strengthens the expander walk turnoff bound. So as I mentioned, the expander walk turnoff bound kind of states that the tails of these two distributions decay approximately as quickly as each other. Our result here shows the stronger statement that these tails actually converge to each other as the spectral expansion gets really good, so as lambda goes to 0, even for a fixed value of c. And I guess we also do generalize our results to Q-ary labelings, which wasn't previously known, and to different expanders at different steps. So we can kind of change the graph at different steps. And that latter generalization will actually be important in some follow-up work. But it just kind of falls out of our proof. So as I mentioned, this problem of bounding this total variation distance was studied a good amount in some previous work. This table basically shows all of this work. And so I guess just to give a summary, this line of work was initiated by Guruswamy and Kumar, who basically completely resolved the question. They showed the big O of lambda total variation bound, but only for the special case of the sticky random walk, which is essentially a canonical lambda spectral expander on two vertices. So like a two vertex expander graph. And their techniques were basically Fourier analysis over the group Z2 to the T. So Boolean, like Fourier analysis on Boolean functions. This result was then generalized to arbitrary graphs by a couple of papers of Cohen et al. And the latter of these papers generalized to arbitrary label weights and did achieve the optimal big O of lambda total variation bound, again using this Fourier analysis on Boolean functions, though they did have this suboptimal dependence on the label weights P. So say if almost all the vertices in this graph were labeled with a 1, then this bound would be suboptimal. So we, I guess, kind of completely resolve this question by getting the optimal big O of lambda bound for all possible graphs and all possible expander graphs and all possible label weights. And we also do generalize to arbitrary Q-ary labelings, which was not covered in prior work, though we make no attempt to optimize the dependence of our bound on Q or on the label weights for Q greater than 2. Perhaps most notably, our techniques are different. So we use Fourier analysis over the integers, like continuous Fourier analysis. And so I guess just to illustrate that, so all these prior works basically looked at the length T sequence of labels you get from the random walk and did Fourier analysis on that quantity, which is a little tricky because then they still have to deal with this sum. So we took maybe the more natural approach in this setting of actually just doing Fourier analysis on the sum of the labels. So now we're taking just Fourier analysis of this integer valued function. And that, for instance, lets us generalize much more easily to Q-ary labelings for arbitrary Q. Though it is true that these results are somewhat specific to symmetric functions. So some of this work by Cohen et al. Was able to look at other classes of functions, such as certain circuits, where our results do not yet apply. Okay, so I'll come back to the proof for symmetric functions, but first I want to overview our results for permutation branching programs. So just to review, a permutation branching program for the purpose of this talk is essentially a read-once branching program where we take in a sequence of T inputs and we store an internal state, which is W possible values. And at each step, we read in the input A sub I, and at step I, we update the state according to a specified permutation acting on the W possible states. The permutation depends on the input A sub I and the step I. So as an example, we can compute the sum modulo 2, or the sum modulo any W, with a permutation branching program of width W. Now, our main result for permutation branching programs is that for every lambda spectral expander G with arbitrary Q-area vertex labeling for any Q, and every permutation branching program, then the L2 distance between the output of the program from when applied to the input of labels, when applied to the sequence of labels from a random walk on our experiment graph G versus the output of the program from a sequence of labels from a random walk on the complete graph J is at most big O of lambda. So big O of lambda L2 bound. And applying Cauchy-Schwarz, we directly get a big O of lambda root W total variation bound. Now, this total variation bound improves upon the big O of root lambda times W to the fourth total variation bound of Cohen et al. Actually, we showed the L2 bound is tight, but we're not yet sure about this total variation bound. So it's an interesting open question, whether for programs of large width, we can improve upon this root W factor. We do show a stronger upper bound for programs that in some sense mix well. So I won't define that here, but you can think of like the sum for some modulo some small w. And in this case, we show that the total variation distance actually decays exponentially with the number of, with the length t of the walk. And maybe most interestingly is that our proof of this result is actually quite concise using this recently introduced singular value approximation notion for matrices. So Cohen et al. Showed this prior bound using, again, Fourier analysis of Boolean functions. Here we let these singular value approximations do all the heavy lifting. So we actually have a pretty short proof that I'll be able to basically completely present in a couple slides. So the first step, which is the first step for many of our results in this paper, is to express the function we want to compute, which here is this permutation branching program with a linear algebraic expression. So we can encode this branching program into a permutation matrix that acts on this vector space, and it simply maps the two. It basically just performs a step of the program. So it maps the tuple corresponding to a vertex v, a step I, and a state j, to the tuple corresponding to the same vertex v, step I plus 1, and the state given by applying the program at step I with input given by the label of vertex v to state j. So essentially, p tilde here is a permutation matrix that encodes the program. And so I guess it shouldn't be surprising that we get this linear algebraic expression for the output distribution of the program. And in this notation, our goal is to prove the difference between the output distributions of the permutation branching program from a random walk on G versus on J. So we can now do this with singular value approximations. So bound this quantity down here. I won't define formally a singular value approximation, but instead just state all the important properties. So first, we know that we have that, I guess the basic property is that an expander graph G, so a lambda spectral expander G, is a lambda singular value approximation for the complete graph with self-loops J. So here I'm, again, interchanging random walk matrices with graphs. And I guess this is just a basic property. So singular value approximations are then also preserved under tensoring with the identity. More interestingly, they're preserved by multiplication by permutation matrices, or actually multiplication by any matrices with spectral norm at most 1. So we can multiply both sides by p tilde. Perhaps most interestingly, they're preserved by powering, so we can power both sides by an arbitrary t, and the level of approximation only really, it only decays by a big O of lambda squared term, regardless of the value of t. And now it's another property of singular value approximations that, given the approximation, we have this bound on the spectral norm of the difference between the two matrices, which gives us what we want. So yeah, so essentially we let this approximation notion kind of do the hard work, and we have this concise proof of our bound for permutation branching programs. So I'll now try to give at least a taste of our proof for symmetric functions. This is not nearly as concise as the proof I just showed. But I guess just to recall, here's the result we're trying to show. This total variation bound is maybe more intuitive, but there's also the tail bound. And our general approach is to change the graphs from G to J, so from the expander to the complete graph, one at a time in a hybrid argument where we bound the difference of characteristic functions at each step. So just to draw that out concretely, for a given step here, we're going to consider the sequence of graphs, a lot of copies of G and then a lot of copies of J. And then we'll compare that to the same thing, but where we switch to J one step earlier. And so we want to look at this vector little g, which is simply the difference between the probability distributions of the sum of the labels from a random walk on G prime versus on G. And of course here we can do a random walk on a sequence of graphs instead of a single graph. There's no problem if we just, at least notation, definition-wise, if we just change the graph halfway through. And in this notation, our goal is to show that the L1 norm of G is at most big O of lambda over T, so that kind of when we do the T, when we change all T steps from G to J, we'll get the big O of lambda bound. Or more generally, we want to show this tail bound. And it is worth noting this 1 over T in the expression is maybe a little surprising because we're basically saying that as T increases, the loss we incur from changing the graph at one step actually decreases. So all the other steps almost make up for this change. And so I guess our goal is to bound the L1 norm of G. First, I'll show how we bound the L2 norm. First, we take the Fourier transform because Fourier transforms are preserved by L2 norms. And then we get this linear algebraic expression for the Fourier transform. I guess I wouldn't try to follow all the math in this slide, but we had a similar expression for permutation branching programs. Now we'll bound this right-hand side above using an inductive argument like Healy used to prove the expander-Chernoff bound. Now, whereas Healy used moment-generating functions, here we have a Fourier transform, so it's definitely a different argument. But ultimately, we kind of bound the norm of each of these factors with induction. And we end up getting this bound on the Fourier transform, which we can then integrate to get a bound on the L2 norm. So now it remains to go from an L2 to an L1 norm. Basically, I won't go through all the details here, but the idea is to kind of bring back in moment-generating functions in order to weight different components in little g according to their distance from the mean. And the idea then is we can partition the intervals into intervals of length, the integers into intervals of length roughly root t. And we can apply Cauchy-Schwarz within each interval, kind of using these weights to select out the values of little g within that interval. And ultimately, we get bounds within each interval, and we sum them up to get our desired bound. So now just to wrap up, so in this work, we obtain improved bounds on the extent to which expander walks full symmetric functions as well as permutation branching programs, so improving upon a line of prior work. Our results do raise some questions. So one is that we showed this big O of lambda total variation bound. But this looks kind of like a central limit or like a Berriosine theorem for Markov chains, which are like expander walks. But the central limit theorem has a convergence rate of 1 over root t. So could we somehow replace this approximating distribution by something more close to what we want and maybe get a big O of lambda over root t bound on the right-hand side? It turns out the answer to this question is basically yes, and this will come out in a follow-up paper. Another natural question is, are there applications of our results back to our motivation? So we were motivated by problems with codes and with PRGs and so forth. So it's interesting whether maybe we can take our techniques, which were motivated by these problems, and actually apply them back to yield new results there. So that's about it. Thank you.